Welcome to Module 1, Automatic Control and the Closed Loop. In this module, we will build the foundation for everything that follows in Book 3. BAS controller is not successful because it sends a command. It is successful when the physical result is measured, corrected, and proven. We will identify each part of the loop, separate command from proof, and learn how to recognize saturation, loss of authority, and broken command paths. Think like a field controls engineer. What did we request, what moved, and what result did the building actually produce? Our learning objectives are practical. You will not only define a control loop, you will be able to walk up to a real BAS system and identify the parts. What is the set point? What is the process variable? What is the controller output? What final device changes the process? And what disturbances are pushing the loop away from the target? We will also separate four ideas that are often mixed together: command, feedback, proof, and physical outcome. That distinction is one of the strongest troubleshooting habits in controls engineering. The engineering principle for this chapter is direct. Judge the loop by the physical result it maintains, not by movement of its output. A valve can move and still fail to deliver heat. A damper can open and still fail to deliver airflow. VFD command can change while the drive is in local hand mode. So the purpose of feedback is not just to make things move. The purpose is to make the result measurable and correctable. The real goal is stable temperature, required airflow, safe pressure, and predictable recovery after disturbances. This is the basic closed-loop control structure. The set point is the desired target. The process variable is the measured condition. The controller compares them and produces an output. That output acts through a final control element, such as a valve, damper, relay, or variable frequency drive. The physical process changes, the sensor measures the result, and the loop repeats. Disturbances are influences the loop does not directly command. Solar load, doors opening, occupants entering water temperature, or a fan starting somewhere else. Good controls do not eliminate disturbances. They reject or accommodate them without unstable behavior. Before troubleshooting or tuning a loop, name the parts. What is the set point? What is the process variable? How is error calculated? What is the controller output? What final element acts on the process? And what disturbances are present? This language prevents confusion. For example, a zone temperature loop may request more airflow, but the VAV damper and the AHU pressure loop determine whether that request can actually be met. When we name the loop elements, we can see where the failure might be hiding. Open loop control is not automatically wrong. If the result is predictable and the risk is low, it may be acceptable. A schedule can enable equipment. A fixed command can operate a simple device. But when disturbances matter, closed loop control is usually required. Closed loop control compares measurement with target and keeps correcting. In a real air handler, both strategies often exist together. A schedule enables the unit, proof confirms fan operation, and closed loops regulate static pressure and supply air temperature. Direct acting and reverse acting can be implemented differently across products. The safer method is not to rely on the label. Ask the physical question. If the process variable rises relative to set point, should the controller output increase or decrease? For cooling, a temperature rise should generally increase the cooling valve or cooling airflow request. For heating, a temperature rise should generally reduce heat. Then verify the full physical response during commissioning. The sign is correct only if the building moves in the intended direction. This distinction is one of the most important lessons in the module. A command is an instruction. Feedback is what a device reports. Proof is independent evidence that something operated. Outcome is the physical result we care about. For example, an AHU graphic may show the fan running because the BAS command is on. But if the VFD is in local hand mode, the BAS no longer controls speed. If current is present but airflow is low, the fan may be rotating but the system may still not be performing. Always ask, what level of evidence do I actually have? A resilient BAS does not make basic equipment protection dependent on a remote screen. Supervisory systems are valuable for schedules, resets, plant coordination, analytics, and operator views. But critical local logic belongs close to the equipment when practical. A field controller should maintain basic temperature control, fan proof, freeze protection, valve action, and safe shutdown, even if the enterprise server is unavailable. If losing a workstation causes the building to lose safe local control, the control boundary needs review. Saturation means the loop is calling for more, but the output is already at a limit. The controller has identified unmet demand, but it cannot fix the underlying capacity problem by itself. In the conference room example, the room is warm and the VAV damper is already at maximum cooling airflow. More output cannot help. The next engineering questions shift to capacity and evidence. Is the airflow measurement real? Is the supply air cold enough? Is the box actually at its physical maximum? Has occupancy or solar load exceeded design? A good controller identifies the demand. A good engineer investigates why capacity is insufficient. Before changing a program, use a structured review. Name the loop, verify the sensor, check the direction of action, stroke or command the final control element in a controlled way. Prove the physical outcome. Then define what happens when the output reaches a limit or proof is lost. This is the professional difference between tuning and guessing. If the valve does not move, tuning will not help. If the sensor is wrong, tuning will chase a false value. If capacity is missing, tuning only hides the real issue for a short time. A maintainable loop is visible and understandable. Operators should see the set point, process variable, output, active mode, proof, and any limiting condition. Trends should include disturbances and boundaries, not just one line. If a cooling valve stays at 100% while temperature remains high, the sequence should identify the sustained response problem. If a server is lost, basic local protection should continue. And during commissioning, do not stop at the screen. Confirm that the physical process responds correctly. Let's summarize. A closed loop connects the requested result to the measured physical process. It compares, decides, acts, and verifies. A command is not proof. A position is not always proof. Proof and outcome must be matched to consequence. When a loop saturates, the controller may be telling us that capacity or authority is missing. Finally, resilient BAS design keeps important local protections available even when supervisory systems are unavailable. In the next module, we will study process dynamics, time, delay, and stability, because even a correct loop can perform badly if we do not understand how fast the physical process responds. Before moving to the next module, pause and answer these questions. Why does a 100% command not prove full capacity? What is the difference between open loop and closed loop control? If a cooling valve command increases but discharge temperature does not change, what would you verify first? And which equipment function should continue locally when the supervisory server is unavailable? For your field exercise, select one loop in a real building and identify the command, proof, and physical outcome. This will prepare you for the next module on dynamics and stability.